All right, so we're going to talk about streams and floods. Running water is a really significant feature on Earth's surface. It's a major agent of erosion, and it carves into Earth's surface and leaves all sorts of signs behind. Even in desert areas, if you take an aerial photo, you can tell where water has run in the past. A stream is any channelized downhill flow of water. When I was a student, rivers were big and streams were little, but I guess it's now all just called streams, but I still kind of stick with the rivers are big and streams feed into rivers. But the river system is kind of important. The Mississippi River includes many other rivers and streams that feed into it. So a river system is all the water that drains into it, so all of the tributaries, all of the other streams and rivers. This is a longitudinal profile or a cross-section through a stream, and you can see on the left-hand side the source or the headwaters. That's up in the higher elevation areas of the stream, and you can see that it's a lot steeper up where kind of B is labeled. Now to the right we have the mouth of the stream, and notice that where C is, that's a pretty flat place. Now in this case the mouth is going into the ocean or the sea. But not all streams make it to the ocean. I could actually pause this. Gradient is a measurement of how steep the stream is. It's a vertical change in elevation over distance. And obviously up near the source we're going to be steeper, and then down near the mouth it'll be much more gentle. In the United States, we measure gradient in feet per mile, so elevational change in feet per distance change in miles. And for a really steep mountain stream, you could even have 800 to 1,000 feet per mile gradients. But the lower Mississippi, where the Mississippi River enters the Gulf of Mexico, that's kind of special. That is so flat. A half a foot per mile. Remember, we still have to have some sort of a gradient because that stream has to flow downhill. So once again, steepest near the source, flatter as you get down towards the mouth. Now, base level is really important. That is the elevation at the mouth of the stream, and the mouth could be the ocean. It could go into something like Badwater Death Valley, well below sea level, or it could enter a lake or a reservoir. So it's not always sea level, not all streams make it there. But base level is important. It's the hypothetical limit to downcutting. No stream can cut lower, downcut lower than its mouth. Otherwise, it'll have to go uphill to get down to the mouth, and that's not going to work. So again, base level is the hypothetical limit to downcutting. So a stream will never downcut lower than its mouth. When a stream is far above its base level, typically up near the source where it's really steep, streams will downcut rapidly. But when they're down near the source where it's kind of flat, they're very close to base level, so they can't downcut. So they're going to put all that energy in lateral erosion, side-to-side movement. Because remember, you got to have a gradient. You've got to have some sort of slope. Water flows downhill. Not all streams make it into the ocean. There are many internal valleys that get streams drained in. The Amargosa River drains into Badwater and Death Valley, and that's 282 feet below sea level, and so it's well below sea level. So its base level is well below sea level. And any river that enters into Lake Tahoe, it's whatever the lake level is, and that's well above sea level. That's a pretty high lake. And that would be its hypothetical limit to downcutting, the elevation at the mouth of the stream. Now, this is a cross-section through a steep section up by the source. When you're up by the source and you're steep and you're far above base level, these type of streams cut a V-shaped valley. So again, where it's steep, you're high above base level, the stream is actively downcutting. But wait till you see the difference. This is what the stream looks like when it's near its source. It can't downcut. It's too close to base level. And so it moves side to side. It laterally erodes. So what we have here is we've got the stream channel. That's where the stream normally is when it's not in flood. But when the stream does flood, it exits the channel and it spreads out, and it actually creates that area called the floodplain. The floodplain is made up of sediments dropped by the stream, because as soon as the stream spreads out, it's going to slow down. And when it slows down, it's going to drop out its sediments. Historically, floodplains have been pretty important. Those are great places to grow crops, but not good places to have buildings, because periodic flooding wipes out the building. So great places for crops. Yeah, occasionally you lose a crop, but every time it floods, it flushes the soil, it adds new nutrients to the soil and new sediments, and it makes it a very fertile area. All right, again, the stream channel is where the stream is unless it's in flood. The stream bed is the bottom of that channel. If the stream was empty, if it dried up, you'd walk along the bottom of the stream on its bed. The stream banks are the sides that contain the channel, and the floodplain are those strips of sediments that have been deposited on either side of the stream channel. When the stream floods, the water exits, it spreads out, and it drops all those sediments, creating the floodplain. All right, so we're going to talk about drainage basins and divides, and I always think of drainage basins as watersheds. So a drainage basin is the total area drained by the stream and its tributaries, so all the water that ends up in the stream. And a divide is a high elevation strip of land that separates adjacent drainage basins. Wait till you see how big it is for the Mississippi River. Now, the Mississippi River drains over 1 million square miles of the United States. It's to the east of the Continental Divide. Yeah, the Continental Divide. Remember that from history class? We learned where the trains met, the ones coming from the East Coast and the West Coast, and they drove in that golden spike. If you drive out on highways to the east of here and you go out and you make it to the Continental Divide, there will be a sign. Everybody likes their claim to fame of the Continental Divide. The Rocky Mountains are a pretty famous part of the Continental Divide. So let's take a look at a picture of this. Check it out. The red dotted line is the Continental Divide. That is, up in the northern area, the highest peaks of the Rocky Mountain. And rain that falls on the west goes out to the Pacific Ocean or the Sea of Cortez, and rain that falls to the east goes to the Gulf of Mexico. You can see it there. Check out the Mississippi River, the Missouri River, the Ohio River, and many other streams and rivers feed into it. It is huge. And check out, there's even a little bit up in Canada. Oh, maybe we'd better be nicer to Canada, because they could pollute a major water system that runs through most of the United States. So look at that. That's pretty cool. All right, so streams erode, transport, and deposit sediments, but they typically don't do all three at once. So a lot of times they're doing 2 out of the 3. And we'll try to figure out kind of what controls what 2 they're doing. And so factors that control which of those 3 scenarios are taking place. Velocity. Velocity is major. You guys know what velocity is. I bet some of you have gotten a ticket for traveling faster than the posted velocity. And so there's a couple of things that control the velocity, or how fast the stream is moving. The gradient. Obviously, it's going to travel a lot faster when it's steep, and typically it's steepest when you're far above base level. We'll also have channel shape. A narrow channel travels faster than a big, fat, wide channel. Channel roughness. A rough channel will cause turbulent flow, and that will slow the stream down. And actually, the more sediment the stream carries, the slower it'll go. But it's kind of weird, because the faster a stream's velocity, the more sediment it could actually carry. So it's one of those strange things. Streams are weird. And then we're going to learn a little bit about discharge, and your virtual river discharge is a homework that you will be completing. And a major part of the discharge formula is velocity. So when velocity increases, discharge increases. All right, so velocity is distance traveled over time. It's the rate at which the water is moving. And streams, a fast-moving stream moves, 3 miles per hour. So if you want to raft down or inner tube down a section of a fast-moving stream, like the North Fork of the American River, and you're like, well, I want you to pick me up in about an hour, but I don't know how far down the stream I'll have gone. You do care about how fast the stream's moving because you want your friend to pick you up, and so you have to figure out. But 3 miles per hour is a typical kind of fast-moving stream, like the American River up in the higher elevations. But when a stream floods, it can be going a lot faster, and you might not be impressed by 15 miles an hour, but a lot of people have died in streams moving 15 miles per hour. That's pretty darn fast. This is important, even if you're not a scientist, because let's say you become a first responder and some kid gets washed away in a stream. You want to know how fast it's moving so that you can go, lower down the stream and get on maybe an overpass and hopefully grab that kid, pluck him out of the water, and save him. When streams are going straight in a straight line, the maximum velocity is in the top and center. And once again, when you do virtual river discharge, you're going to get to play with this and actually do some measurements, and you'll figure this out. It kind of makes sense. They're not going to go fastest on the bottom or the sides because of friction, drag. They're dragging along the bottom or sides of the channel. And so top middle is where they travel the fastest. Now streams take curves. Picture in your mind a nice curving, meandering stream. And it's kind of like a ride at Disneyland. Check it out. So what we're looking at is a stream that's running from top to bottom. And as it goes into a curve, the area of maximum velocity gets thrown to the outside of the curve. Just like if somebody was driving real fast and you're in the back seat with no safety belt on and they take a big corner and they make that turn, you get thrown to the outside of the curve. And so it's centripetal force. It's kind of important. But what happens when this happens is, where it says A prime, A with that little dash, right towards the top, that's the cut bank. And the A on the other side of that line is actually the depositional. Because if the area of maximum velocity moves to the A prime area, then the velocity drops where it's A. And so you can see that in that top picture. That's a cross section through the stream. Okay, in the B section, the stream is just traveling straight, and there's that maximum velocity right in the center. And then down by C, where that cross section through the stream is, look at where the cut bank is. It's on as the stream travels down our screen. The cut bank is on where C is, and the depositional bank is the C prime. So that's actually how a stream laterally erodes, and we'll see a lot of that happening down by its mouth. Remember, it can't downcut anymore. All right, velocity is really important in determining whether a stream will erode, transport, or deposit. If a stream's moving really fast, it can do a lot of erosion and transport of sediments. And if a stream is traveling really slowly, it's going to be doing a lot of deposition and maybe just transporting the littlest sediments. All right, so high velocity means high energy, and when that stream is in high energy and high velocity, running really fast, it's going to mostly do erosion and transport. But when it's traveling slowly, low velocity, low energy, a whole lot of deposition. So we're going to take a look at something called Holstrom's curve. It's something very important. And we'll try to understand kind of how we determine what's going on in a stream, what size sediments it's carrying, at what velocity, etc. All right, now Holstrom's curve is kind of interesting, and I'll probably try to make a YouTube video so I can kind of walk you through with a pencil and show you, but it's on the next slide. We're going to talk about it. But we have different sediments. You should remember this right from sedimentary rocks. Remember small, medium, and large, small being silt and clay, sand being medium, and gravel plus being large. Well, to erode a sand-sized particle out of sandstone, you actually need more energy than you would need to actually, once it's eroded, transport that sand grain. And so we're going to take a look at that relationship. And then, there'll be a velocity where the stream drops beneath it, and when the stream velocity drops, it will no longer be able to carry that sand grain. So when we look at Holstrom's curve, let's go ahead and look at it, check it out. It's a bunch of curves. Now, you guys, this is saving you a lot of calculus. If you can come in on one side where it says stream velocity in centimeters per second, and then on the bottom it has grain size. Clay and silt are the smallest, clay smaller than silt, and then you have sand, and then you have gravel. Now, notice that red arrow and red kind of dotted line. The velocity that we would need in order to erode the sand grain out of sandstone is up in the green where it says erosion. So we have to be above that black line that cuts erosion off from transport. And so you're going to have to do some guesstimation. If you take your straight line over from right in the green area, I don't know, 50. We'll call it 50 centimeters per second. And in fact, you guys, it gets a little bit more complicated. That's actually a log, semi-log. So it's a base 10 thing, but we'll just call it around 50. So you need to have 50 centimeters per second to erode. But now let's say I have the sand grains eroded and I drop down to 10 centimeters per second. I will no longer be eroding sand out of a sandstone, but the sand that's already eroded can be transported. Now, if my velocity drops below 1 centimeter per second, I am going to start depositing the sand. I can't even carry the sand grains that I have had. So that's just the example. You're going to need a higher velocity to actually erode out the sand grain. And then, when the velocity drops, we're going to stop eroding and we can still transport the sand grains, but there is a point that when the velocity drops below that about 1 centimeter per second, I'm going to be depositing all of my sand grains. Now, check out clay. Clay's a little weird. I need a lot of velocity to pull those clay particles in shale apart. It's kind of like static cling. The clays stick together through molecular cohesion. This is why I always put bounce in my dryer, okay? Because otherwise my socks stick to the butt of my pants, and when you pull it off, that static cling, that's kind of what it feels like to pull clay particles apart. And so you actually need quite a bit of velocity to pull them apart, break those ionic bonds, that molecular cohesion between clay. But once you have clay being transported, your water can practically come to a standstill. I call clay the magic carpet ride mineral, because it actually, when it enters into the ocean for a stream, it can move for 50 years before it drops out. So check that out. It doesn't even drop out in that picture because clay is really wacky. So surprisingly, you need a lot of energy, as much as you would need to pull gravel plus out of a conglomerate. But once you have it moving, it's almost impossible to drop out. All right, so this is kind of talking about that clay and silt. They are weird. It's quite a surprise. And it's just because how the clay and silt stick together. It just makes it harder to pull apart. But once they are apart, they're hard to deposit. They will, every single river, no matter how wimpy it's running, will be carrying silt and clay. They're, the water has to basically come to a standstill before they ever drop out. All right, we're going to just take a quick look at channel shape. Obviously, check this out, you guys. The top one will travel faster than the bottom. It's, again, friction or drag. We have more surface area exposed of the water to the sides and bottom on B than on A, and so it's going to slow them down. All right, let's also look at channel roughness. This makes sense too. Remember that really smooth stream channel? The flow will be more laminar. Here, it's going to make it kind of turbulent eddy. It's going to make it rough and choppy. And so channel roughness also, it can slow down a stream. All right, so here is the formula for stream discharge, and I'll always give this to you. You guys are going to really get to know this pretty well from virtual river discharge, but discharge is equal to the width of the stream times the depth of the stream times the velocity of the stream. The width is in feet, okay, because we're in the United States. The depth is in feet, and width times depth is basically the area of the stream. And now we're going to multiply that by the velocity in feet per second. And so discharge is measured in cubic feet per second here in the United States. In other countries, it's cubic meters per second. All right, so if you have a stream that is traveling at 6 feet per second, and it's 100 feet wide and 10 feet deep, you can figure out the discharge pretty easily. 100 times 10 is 1,000. That is the area of the stream, so 1,000 square feet. And now we're going to multiply that by 6 feet per second. So we're going to have 6,000 cubic feet. So that's to the third power per second. That would be our total discharge for the stream. All right, I looked at this slide. I'm from Southern California. I moved up to Northern California, and I'm like, wow, I wonder if I can figure out when they first put in Folsom Dam. I didn't even have to look it up. I just looked at this slide for discharge. We put dams in to control flooding events, but dams only control short-term flooding events, not the big ones. And so if you look somewhere around, I don't know, 1957, 1958, do you guys see where all the kind of little background flooding goes away, and we still see the same peaks, the really big ones. But, you know, it kind of controls just those yearly small floods. But the ones that go all the way up, in fact, in the 1980s, like 1986, 1987 was a huge one, and I have a video of that. We almost lost Folsom Dam. You know, we could have lost thousands of people. We were very lucky, and I have a video of that, and I talk about it in my face-to-face class, and can't figure out a way to give it to you guys, but oh, was it scary. And the sad thing is, it could happen again, and, you know, don't complain when they let a lot of water out of Folsom Lake before the rainy season, because that's the only thing that saved Folsom Dam and saved all those people downstream, including Sac State, and, you know, the whole campus would have been underwater. So, you know, I don't know about dams, but dams, we put them in for flood control, to have a water source when we're in a drought. Recreation, I mean, that's a big industry. Oh, hydroelectric, it is a clean energy. It does mess with the organisms that live there, though, like the fish and things. All right, so let's talk a little bit about what type of sediments are carried by stream and how they're carried. The total load carried by a stream is all the sediments carried by a stream. They're in 3 different parts. There's the bed load, the stuff that bounces or drags along the bottom or rolls along the bottom. There's the suspended load, and silt and clay are almost always in the suspended load. And then there's the dissolved load, otherwise known as the invisible load. And that is all those ions in solution, the products of chemical weathering. Water is a chemically active molecule, and it does its job. And even if you got a mouthful of stream water and you didn't go, ooh, yuck, tastes like the ocean, this is what's going to make the ocean salt. It's going to carry all that stuff down to the ocean, and it's going to get concentrated in the ocean. So we'll talk about that. But again, the bed load is the stuff that, you know, it differs depending on the velocity of the stream. The stronger the stream, you know, the less stuff you have in bed load. But the weaker a stream, maybe, you know, you don't have any bed load. I guess it kind of depends. But bed load is where the larger, heavier material that it either rolls or drags or skips along the bottom of the channel. And here in this picture, we can see it. See the rolling, sliding, and even it says sand moving by saltation. That's not part of the water column. That stuff, it gets a little turbulent eddy, it takes a little ride, but it ends up bouncing back off the bed of the stream, and so that is part of the bed load. All right, the suspended load is whatever is light enough to stay in the water column without bouncing off the bottom. Pretty much always silt and clay, but if your stream is traveling really fast, it could be a lot bigger material. So pretty much all streams carry some suspended load. All right, so you can kind of see it there, silt and clay, suspended load. But the dissolved load, you don't have to memorize these, you guys, but it's, calcium, carbonate, sodium, chloride. It's all the different things that we're going to talk about that make up kind of the chemistry of the ocean. It comes from the chemical breakdown of ionic bonds in rocks. And if a stream flooded a little bit and you had those kind of little pockets of water on the side and then they evaporate, you actually have white crusty stuff, and it probably wouldn't be table salt type stuff, but we would make a evaporative sedimentary rock. It's kind of interesting. So again, this is going to come to play later on, because this is what ended up making the ocean salty, is the dissolved substances that are carried by streams off continents and even off the seafloor and things like that, and concentrated in the ocean. All right, streams erode the rocks and sediments over which they flow. They can cut their valleys deeper, especially up by the source. They can widen them, especially down by the mouth. And, they a lot of times over steepen their sides, and the material that mass waste in does get carried away as part of the sediment load. All right, there's 3 different ways that streams erode: hydraulic action, solution, remember it's a chemically active molecule, and then plain old abrasion. Now, I always think of hydraulic action as a pressure washer. Be careful, if you go get a professional pressure washer, it can really hurt you. It can really mess up your deck. The type you buy just to wash your car. They're pretty wimpy typically. But especially like at a waterfall where the water falls over a cliff, and then it's kind of like having a super powerful pressure washer. And if there's any cracks, like if your driveway's full of cracks and you get one of those big professional pressure washers, you can trash your driveway. Don't do it. If you try and pressure wash it, because the water, the hydraulic pressure of the water, if it finds cracks and breaks, it's going to just blast that rock apart. And at the base of waterfalls, you typically have a big plunge pool. And so down in Southern California, where during the summer, we either don't have waterfalls or they're very wimpy, you can actually go swimming in those plunge pools. It's fun, but be careful, not up here maybe where we have lots and lots of water. So again, just imagine that that's my cracked driveway and I got my professional pressure washer. Oh, whoops. Because just like the pressure washer is under pressure, the force of the water is Mother Nature's pressure washer. And any cracked rocks have lots of cracks in them, it will find the weakness and blast apart the rock and erode it. All right, here's a pretty large part of the Niagara Falls, and at the base there's a big plunge pool. I think it's Last of the Mohicans in that movie. They show the people hiding behind the waterfall, and that's part of the erosional process that a waterfall goes through. All right, water is chemically active. We talked a lot about that. Water will break apart ionic bonds. Water running over limestone, if that water is slightly acidic, it just rips that apart. Also, sometimes sandstone could be held together by a calcareous cement, calcium carbonate. Water will work its lovely action on that too. So water is a universal solvent. We're going to talk more about that later. And any ionic bonds, water will get in and break apart. All right, then there's just abrasion. When you're carrying sediments, it's kind of like sandpaper. The coarser the sandpaper, the more wood it takes off in once. And the more coarse the sediment that the river's carrying, the more abrasive it is. So the more sediment you're carrying and the larger the size class, the more abrasive this stream channel can be. Now this is pretty cool. This is a pothole that I go to. It's at the southern end of Highway 395, south of Mammoth Mountain, kind of down almost to LA County. And this is called Fossil Falls. There was a giant waterfall and a dam broke, back during the Ice Age. And you got a turbulent eddy. And in that turbulent eddy, which is a little swirly pattern of water, you had some coarse grained material. And it just kind of drilled right on down and made made this really cool pothole. And the sides are smooth, and sometimes we play a little bit on there on our field trip to see if we can climb it. It's very hard to climb because it's so smooth. Now, at the end of the major ice age, remember the continent of North America was covered in ice, and this was actually a major, Mother Nature dam break up kind of in the St. Lawrence Seaway area. And this is dangerous. I wouldn't let kids play on this, students play on this. But once again, the turbulence with the sediments, it just scoured these potholes. So that's kind of cool. That's a big scale. All right, streams do erode also. They cut down. We already talked about down cutting. It's done mainly at the source. It cuts side to side, especially near the mouth where it can no longer down cut. And then we're going to talk about headward erosion of a stream and maybe headward erosion of a waterfall. Waterfalls also headward erode. All right, so again, down cutting, it's when you're up where it's steep, you're up at near the source, you're far above the base level, a stream will cut down. Now, the slot canyons are pretty famous. There's some famous slot canyons in Arizona and Utah. If you guys saw, what's it called, 127 Hours, the actor guy was kind of, I thought, what's it called, canyoneering, going through one of those slot canyons when he got in trouble. So yeah, that's an area there where the stream is really rapidly down cutting. All right, and here's some lateral erosion. When you get into a flat area, the stream can't downcut so much, and so it starts to be like an angry snake. If you pull an angry snake's tail, it does all these big swirls and curves, and we call this a meandering stream, and you can kind of see it happening, and it's creating its own floodplains and everything. And we talked a little bit about the centrifugal force and being the cutting edge and the depositional edge and things like that when we saw a curving stream and where the maximum velocity area is. And so this is how a stream would widen its stream valley over time. So lateral erosion, the energy has to go somewhere. It can't go to down cutting. So what it's going to do is go to laterally side-by-side erosion. All right, and then headward erosion. As long as there's higher elevation land to go into, that stream will continue to cut into higher ground. And if you're going to buy some property up in, the higher parts of the foothills, maybe Colfax or somewhere up Highway 80, or even where I live in Auburn, I would make sure that there's no stream headward eroding your way because you can't stop it. Headward erosion leads to one of my favorite things, stream piracy, or it can. And we have a great example up Highway 80. If you've ever been to that Immigrant Gap, I don't know if it's a rest stop or an overlook site, it's kind of a neat area. But right there, what you're looking at when you look off to, I guess it would be the west, is you're looking at the Bear River Valley. If you guys know the Bear River, if you go out on Highway 49 towards Grass Valley, you actually cross over it, and it's not a huge river. It used to be, though. And the Yuba River didn't used to be a big river. Now it is. And so just above Immigrant Gap rest area is a notch where the Yuba River headward eroded, and it headward eroded into the Bear River. And it stole all the upper drainage area of the Bear River, and so nowadays the Bear River is a little wimpy river and the Yuba River is a great big river, so kind of cool. All right, another thing is right at the end of the last ice age, Niagara Falls was where, see where it says Niagara is in escarpment in the Niagara Gorge, so go kind of to the left of that, that's where Niagara Falls was. But Niagara Falls waterfalls also headward erode. And it's kind of scary because, it's actually happening at a pretty fast rate. It's about 1 meter a year. And Niagara Falls is pretty famous. If your family was from back east, somebody in your family spent their honeymoon at Niagara Falls. It's a big honeymoon spot, at least used to be. And as Niagara Falls headward erodes, it will headward erode into Lake Erie. That will cause one of those massive flooding events that will cause some great big potholes to be cut. It won't happen for another 27 or so thousand years, so don't worry, but boy, if we're around in 27,000 years, we might not want that to happen. All right, so streams deposit. They deposit when their energy drops, and sometimes streams temporarily deposit. Our area is famous for placer mining, stream deposit mining. And things like gravel and sandbars, those are temporary deposits. So I have to mention them. It's not a test question or anything, but just because, somebody in our class, their great-great-grandfather or somewhere back in then came to California or came to this area to look for gold, and maybe was a river deposit miner. So I'll show you guys a little bit about stream bars. Here's some in Santa Barbara where once in a while we actually do have water running. We get some heavy rains, and it will actually pick up and move the gravel bar or the sand bar, and then when the water levels drop them out again. So it's not really an ultimate deposition, but gravel bars are pretty cool. All right, again, it's a temporary thing. I'm going to kind of move through there. Let's go ahead and talk about stream channel pattern. Streams can run straight. I'm actually a really big fan of braided streams, but stream channels that run straight are typically steeper areas. We're going to talk about braided. When you go from a steep to a flatter area, this is often braided. The stream will become braided because when the stream slows down, it'll drop out some of those gravel bars or sand bars. And then in areas that are very flat and very close to base level, the stream will be, doing the snaky S thing and doing a lot of that sideways lateral erosion. All right, again, straight stream channels, you're flying over, you look at a very straight stream. It's typically in a very steep area, although it could be following a fault. The San Andreas Fault has lots of streams that follow it, and so they look really, really straight, even if they're not steep. So there are other things, but typically it's where it's steep that it's straightest. All right, I love braided streams. Think about going salmon fishing, or think about the pictures that you might have seen of grizzlies going salmon fishing up in Alaska. And, don't fall in love with a gravel bar, because next flooded, rainy season, that gravel bar will be picked up and moved. So these are typical of places. So here's a braided stream in cartoon. I'll show you a real picture. But as the stream flows from left to right, the stream will widen, or it could hit softer rock, or it could hit flatter ground, and the velocity drops. And if the velocity drops, it's going to drop out the sediments that it's carrying, and those, it looks like sand or gravel bars, and the patterns over time change because these are temporary deposits. All right, we find a lot of braided streams. Alaska, remember in Alaska you have lots of ice during the winter, you have steep, very big mountains, so lots of erosion happening, lots of glaciers upstream, so high sediment load, high variability in discharge. So those streams, some of them are frozen solid in the winter, but boy, as soon as that spring thaw comes, they come charging down. And then, weak bank material, or you go out into flat areas. And here's a pretty Alaskan braided stream. Probably some good salmon fishing on those gravel bars down anywhere in this picture. Pretty cool. All right, and here's an area. Boy, this is meandering. This is flat. I bet there's a lot of mosquitoes here. And so again, if you're down by base level, you're down by the mouth, you can't down cut, you still have energy. So it goes into lateral cutting. And once again, how that happens, you have the cut bank, you have the depositional bank, etc. And a stream will go from, A to B to C, and just keep doing that. And eventually you could make too much of a loop, and then we could end up with a cutoff. Now, I'll show you cutoffs here in a second, or oxbows and things like that. But, here's a section of the Missouri River going through the Midwest that's doing some of these great big curves. All right, actually, so in this case, we can see we're a meandering stream. It's too much work to take that huge out of the way. It takes a shortcut. Next time it floods, it'll take a shortcut. And in the real picture, you can see where one of those meander bends has been cut off. And where there's water in it, it's called an oxbow lake. And then when it all dries up, it's called a meander scar. So kind of neat. It's neat to fly over the country. Get the window seat. Hopefully it's not foggy, and you look out and you can see lots of cool stuff like this. All right, I'm going to kind of skip through here, you guys. Floodplains are historically very important. If you have a shopping list at IKEA, before we have a really rainy season, get that shopping list done. I fully expect if I live to be as old as my dad, and I live here, I will see the first floor of IKEA flooded. When water levels are really high, drive over on 80 over the Sac River, and you're like, wait a sec, the river is higher than the IKEA parking lot. Yeah, there's a levee between them, but remember, our levee system is really bad. So, we could have a catastrophic flood, and at least the first floor of IKEA could get really flooded. And, floodplains, we're not meant to, it's a floodplain, you guys. IKEA's in a floodplain. It's not good. The floodplains are where we should be growing, rice and crops and things, and occasionally we'll lose one, but a crop. But, much better than big buildings and houses and things. So again, when the stream floods and it leaves the channel and it widens out, remember all that drag, it slows down and tons of sediments fall out. And so here we go, we got a stream, it's in its channel, then it goes into flood. Wow, it's a pretty big flood. And actually, you can actually see the natural levees. The first stuff to fall out will be the biggest, coarsest stuff, and that falls out right by the stream banks. And so the next time the stream has high water, it actually might not flood. It might be contained in its natural levees. Obviously, we see what Mother Nature does, and we copy her, and we make these like 50-foot levees that just are not structurally safe. So again, knowing your floodplain zones, this is why I let you guys have the option of doing virtual river flooding as extra credit. If you live in Natomas, I don't even know if you can buy in Natomas anymore, but they might force you to buy flood insurance. You are in a very dangerous flooding area. You guys, honestly, I would not live lower than Rockland, and I'd be very careful anywhere I live being too close to a stream. I live at 1,500 feet, and I'm pretty happy to live at 1,500 feet. I can't get flooded at my house because I am at the top of a hill and all this stuff. You need to carefully choose where you live. So understanding the flood zones and the probability of the different floods and if you should buy flood insurance, that's kind of all with that. All right, and again, yeah, levees are good, but you can't make them too high. They become structurally unsafe. All it would take is a gopher or a tree falling over to wreck your levee. And you guys saw what happened when levees broke. That was New Orleans and Katrina. Most of the damage was actually caused by broken levees. And you think their levee system is bad, ours is worse. So we could have some severe flooding in our future. Be careful what you buy. Your house is your biggest monetary investment, and your family should be the most important thing to you. You want to live somewhere safe. Don't live in a flood zone.